So let me finish this discussion here, and then I'm going to the next slide here. So this argument does not apply when gamma have subgraph divergences. And the reason is, as I discussed already, that although is polynomial, f k P m mu is not. In fact, FEK, I think I have written the notation FEK. Yes, so this this is, there is a K subscript. So this FEK is not a polynomial. We just proved that this is a polynomial. This is not a polynomial. And we know that this will involve, so involves terms like log p square by mu square and log m square by mu square. We have seen that already in many calculations. We have just shown this here. So this is the finite piece. So although the residue has the expected form, but the finite part, which f is, has log m at square, and in higher order terms, higher order diagrams, even log p square by mu square will also appear. Okay. Now, suppose, so what do we do in this case is the question. Now, suppose gamma contains subgraphs gamma 1 and gamma 2 with superficial degree of divergences, omega 1 greater than or equal to 0 and omega 2 greater than or equal to 0 respectively. If gamma 1 and gamma 2 are individually free of subgraph divergences. So we have a gamma, we have a graph gamma which has subgraphs gamma 1, gamma 2, and gamma 1 and gamma 2 have superficial degree of divergences, so positive or 0, so they are divergent. But gamma 1 and these subgraphs do not have any subgraph divergences. So then we may write, we can apply the same result for gamma 1 and gamma 2 individually. Then gamma will be having this structure. Sorry, I might have made some mistake there. Let me check the form. So there is no K here. Sorry. Because there is no summation. It is outside the summation. So there is no K here. So this is coming from the gamma 1 subgraph. And then there is a gamma 2 subgraph, which will contribute 1 over epsilon to the power k2 times r2 k2 plus k2. This individual sum over k1 and k2 will go over the loops, number of 1 to number of loops, say L1 and L2. If gamma 1 is a L1 loop graph and a gamma 2 is an L2 loop graph. Now, so now if when you multiply this, then you get terms like this multiplying F2 and this multiplying F1, these cross terms will have poles, but with F1 and F2 appearing in the residues. So this will lead to pole terms with residues containing F1 and F2, hence terms like E square over mu square and M square over mu square. This kind of a situation are usually known as the issue of overlapping divergences. Okay. So Toft and Veltman in Nuclear Physics B44, 1972, 189 to 213 explicitly shows cancellation of log terms in two-loop overlapping divergences. Where the argument is generalizable to higher loops. Okay, and we have seen in some in the 2-point function calculation at 2 loop that all log m hat square, which is basically a ratio of m square and mu square, all log terms were cancelling and this will continue to all higher orders. And this proof, this argument, Toe's development argument shows how that in any arbitrary graph, if you have a two-loop subgraph where these overlapping divergences appear, then the log terms will cancel, and this argument can be generalized to arbitrarily high loop orders, and that makes it that. So when you prove that, then you come back to this. Then you see this statement. This claim is true for all diagrams. All these gammas that the residues will be homogeneous polynomial in P and M of degree at most omega. So that will complete the entire proof, which we'll not do here. Now, this result is extremely important because this shows that the counter term renormalizable as a program works, because it is this, because of this polynomial nature, you can absorb these divergences by counter terms in the Lagrangian, which are of the usual type, local Lagrangian. And because if it is a polynomial in P square, then those are converted into some derivatives of phi. In, for example, in the renormalizable situation, when we have phi-fourth theory in 4 dimension, which is renormalizable, we have only the this 2-point function and 4-point function, and the 2-point function will have mask dimension 2, and all the residues should have the p square dependence should be only p square and m square, and this p square term will this counter term, corresponding counter term, will be exactly looking like the kinetic term of these original Lagrangian del mu phi, and the m square term will be the mass counter term, and the other diagrams, which is the 4-point function, those counter terms will be having p square to the power 0 and m square to the power 0, but arbitrary higher powers of lambda, and those will be correcting the lambda phi-fourth interaction. And so for a renormalizable theory, this is because of the restriction that the residues will have maximum the residues are polynomials with maximum degree omega, and since there is a, for renormalizable theory, the spectrum of omega being positive is finite, and then there is only a finite number of terms for which this kind of residues will appear, and they are exactly the same terms that are originally present in the Lagrangian. For non-renormalizable theories, since omega, the spectrum of omega is not finite, I mean the positive omegas, there are new divergences. So there are no limit in what kind of the degree of the polynomials, and therefore all sorts of correspondingly all sorts of couplings and including derivatives will appear in the counter term Lagrangian. And as long as you allow infinite number of couplings, these are also counter term renormalizable theories, what we call non-renormalizable theories. These are as a counter term renormalizable program that goes through. So it is a consistent theory in that sense. It is just that it has infinite number of couplings as opposed to a renormalizable theory, which has only which has the same number of couplings as in the classical action. Okay. This was mentioned earlier, I think, in a discussion session, but I am mentioning this now in the lecture as well. So let me just write down the basic point here. So this result is extremely important. This is also true for, this method works, and it's also true for non-renormalizable theories. And in this sense, non-renormalizable theories are equally renormalizable. So long as we allow for an arbitrary number of couplings. This enables one to physically interpret theories as low energy effective field theories. We will see that, I think, more in more detail later. How it's a low energy effective field theory, how we can view it as a low energy effective field theory will be seen, and we'll probably have a more detailed discussion later. I don't want to go into clarifying that point right here. So finally conclude, we can conclude the following, that for phi-fourth theory in 4 dimension, since we have only two primitive divergences, omega equal to 2 and omega equal to 0, and all counter terms for phi to the power 4 in D equals 4, all counter terms the counter term diagrams are of these following two categories. So I have used cross vertex for 2-point counter terms. So now I'm adding all those 2-point counter term diagrams, and after adding them, I call it a single cross, and that will have a structure k equals 1 to infinity 1 over epsilon to the power k, sum over L equals k to infinity lambda to the power L p square times kl of f epsilon m by mu g epsilon m by mu. And adding all the dots vertices, we will have a structure lambda mu to the power epsilon. So let me explain these two equations. So first of all, we know that a diagram with at a loop level L will have a maximum pole at L. The same thing can be rewritten in this order, in this following fashion. If you check, so the value of L, for example, is k, k plus 1, k plus 2 up to infinity. So if you fix the value of L, then you can calculate the corresponding values of k. So k will be 1 to L. K, so if L equal to k will be 1 over epsilon to the power L. Then there is a term L equal to k plus 1. So then you solve for k, that becomes L minus k becomes L minus 1. So there is a term epsilon to the power L minus 1. Similarly, 1 over epsilon to the power L minus 2, and so on up to 1 over epsilon when k equals 1. Okay. So for at a given fixed L, you will always have 1 over epsilon square, and up to 1 over epsilon to the power L. So I have written this summation in a different order here, but you can check that it is same as what we wrote, what I wrote earlier for a fixed L. Now I am adding all these diagrams, and I can rewrite it in this form. Now for all these poles, for each given pole, I have the summation over loop summation, and that loop summation, depending on the value of the loop, there will be different residues. The residue will be multiplied by p square and m square because of this, because of the claim that the residues are homogeneous polynomial of p and m, and this or the dimensional analysis that R has m to the power d times dn times the lambda to the power L, and etc. And then there are coefficients these coefficients will be dependent on the finite ambiguities that we had at lower order terms. So if you remember, if you go back to the actual calculations at each level, when we introduce a counter term, we introduce a finite ambiguity in that, and that finite ambiguity will be involved in the residues at next orders. So this is why you have dependence on that. I can check explicit examples. You see here the counter term Lagrangian I'm showing here. So at lambda square, you have counter terms which depends on f1 and g1, which were the f1, g1 were the finite pieces in the previous order. You see, so this finite pieces that and finite ambiguity in the counter term that happened that appeared in order lambda became inside the residues, came into the residues at the next order of a pole. Okay, so similarly this f2 will go into the residue of the next order in lambda in certain poles. So that is the pattern, and of course this way you will always collect the counter terms. Besides the poles, there is always a counter term which is finite, and you have to collect all of them. Once you add, you have the finite terms. So that each equation has a finite term, which is a finite ambiguity in the counter term. Same for the 4-point functions. It is the same explanation. So this is the general structure of the counter term for phi-fourth in d equal to 4, and that will be the feature for any renormalizable theory. We have to just get the if the interaction is renormalizable, if the coupling is dimensionless for a theory in a particular dimension, you will find the spectrum of primitive divergences, in this case omega equal to 2 and omega equal to 0, and correspondingly you have infinite number of diagrams corresponding to each one of them, and those infinite number of diagrams can be at level by level, you can remove the singularities of those diagrams by adding counter terms, and these are always going to be polynomials. The residues are always going to be polynomials in p square and m square, as I just discussed. The log p and logarithmic terms will all cancel because there exists a general argument, and this is the counter term renormalization program, and that's it. So